Good evening, everyone. Thank you to the organizers for giving me the opportunity to speak. My name is Ananth Rajan. I'm a chemical engineer at IISc. I mainly work in molecular simulations and density functional theory of materials, but I'm also interested in statistical mechanics. So today I'll talk about how considering a relative energy window impacts the analysis of small systems, systems with very few particles in microcanonical statistical mechanics. So there are well-noted challenges in defining entropy in small systems, and these have been the subject of discussion over the past almost 100 years. Although the microcanonical ensemble, at least for classical systems, is less investigated, it is still important, and especially for quantum systems, it's quite important. And here, an intense debate has been what W, right? What number of microstates do we choose when we write S equals K log W? Because we all know that S is minus K some Pi log Pi. It's also Kb log W in the microcanonical ensemble, but what W do we choose? And there are two alternatives. There's something known as the Gibbs volume entropy, which says that we need to take all the states that have energy less than E. And then there is Boltzmann's surface entropy, which says that you should take only the states in this thin sliver, which are the states centered around energy E, but within an energy window epsilon, fixed energy window epsilon, right? And mathematically, that's how you can write it. S is Kb log W, that's the area under the density of states curve. This you can write as del omega del E times a fixed energy window epsilon. Now one can ask, isn't energy fixed to a exactly specified value and we only need to look at degeneracies? And the answer is, as soon as you say that you're looking at any of these two entropies, you're already allowing some variation in the energy. So energy is not fixed actually, right? There is some variation. There's a lot of variation in this particular ensemble, the Gibbs volume entropy. There's some variation here. So if you read some of the textbooks, they'll say that almost every system has some contact with its surroundings, however little it may be. Thus, you do need to consider some changes in the energy. Now, the main point of contention is the possibility of negative absolute temperatures. And this has been seen. I mean, some would say it is a non-equilibrium state, but it has been seen that there are states when you increase the energy, the entropy actually comes down. And this is definitely possible in bounded energy systems, right? When there's an upper limit on the energy, as soon as you go to very high energy states, you will start reducing the entropy because only the high energy states will be populated. There's order, entropy comes down, and temperature is negative, right? So this is seen in nuclear spin systems, lasers. There are two particularly famous experiments. There's also Purcell and Pound from almost half a century ago, right? And of course, many of you may know, but negative absolute temperatures are hotter than positive infinity Kelvin. So people often think of the hotness, which is minus beta, minus 1 over kT. This is a continuous scale. You can see it goes from least hot to most hot, but that goes from T equal to plus 0 Kelvin to T equal to minus 0 Kelvin. So it's a bit strange to think about. Now, these are the issues plaguing Gibbs and Boltzmann entropy. Gibbs entropy entirely disallows negative absolute temperatures because it's defined as the volume, right? The number of states always increase, right? You can never have the number of states go down. However, this is in disagreement with experiments, and this has been noted. Boltzmann entropy, on the other hand, it's good. I mean, it is able to predict negative absolute temperature, but also does so for systems where you would not expect it. You wouldn't expect like an ideal gas or a quantum harmonic oscillator or particle in a box, right? Systems with positive energy to suddenly show negative temperatures, right? So this was noted by Dunkel and Hilbert in their Nature Physics. It was, I mean, I think a lot of controversy was there around that, right? So at that time. So when I looked at all the possible entropies, this is how I thought we could visualize it. You plot the spectrum here, E naught and E max. So Gibbs entropy considers all states with energy less than E. This is Boltzmann entropy, consider all states with energy within a fixed energy window. And then I sort of said, let's look at two other cases. This is the degeneracy entropy. So you'll consider states exactly at energy E. So in some sense, the fluctuation allowed, sigma E, is exactly 0. And for reasons I'll reveal, I decided to consider a relative energy window, right? So the window scales with energy E, and note that this window is lying in between two eigenstates, right? So what that means is there is some uncertainty in knowing exactly the energy of that eigenstate, and this orange width is representative of that particular uncertainty. Right, so this sort of leads us to this relative energy window or relative energy constrained Boltzmann surface entropy. So instead of del omega del E times epsilon, it's del omega del E times epsilon RE. Subscript R means relative, right? And this is sort of I tried to justify by the Heisenberg energy time uncertainty principle. So any eigenstate, you will know the energy exactly if you measure it over infinite amount of time. Try to probe it, right, to know the energy over a finite period of time, the uncertainty will go up, right? So that's this uncertainty. And if you have an eigenstate thermalization time, it's inversely proportional to system energy. For small systems, that's like a lower bound. Then you could have this sort of a construct. Right, so these are the kind of predictions you can get for an ideal gas and a particle in a box. Because at high temperatures, you can take derivatives, everything is smooth. But I wanted to also look at low temperatures. Here, you can't take derivatives, so you have to somehow discretize it, right? So T is delta E delta S and omega is delta omega delta E times epsilon R E, right? These are the kind of predictions you get. For a 3D ideal gas, degeneracy entropy is not defined. There's no state with exactly energy E. Gibbs gives 3n by 2 kT. Boltzmann, well known, 3n by 2 minus 1 kT. The proposed and the canonical both give 3n by 2 kT. So it looks like the proposed and the Gibbs match canonical, whereas there is some minus 1 here. That's the reason for the infinite and the negative temperatures for an ideal gas. If you look at a particle in a 1D box, again, Boltzmann is minus half kT, which is a bit weird. Degeneracy, again, doesn't work. Again, Gibbs proposed and canonical seem to point to the right direction. Right? So what's happening here? Can we sort of say which one is better, the Gibbs one or the proposed one, right? In terms of making sensible predictions for small systems. For large systems, it doesn't matter, right? 3n by 2 minus 1, 3n by 2, everything is the same. So I looked at a quantum harmonic oscillator. The spectrum is very well known, total number of states, right? So when you do the math suggested on the previous slide, you look at the Gibbs entropy, it misses the ZPE. Cannot predict the ZPE. You can plot E versus T, you see that it starts at 0, right? So that's a so-called Planck oscillator as Patria calls it, right? Misses the ZPE. But if you look at the relative energy constrained Boltzmann entropy, it gets the right ZPE and the canonical prediction. However, if you look at the Boltzmann entropy, this was also documented by Dunkel and Hilbert, it predicts infinite temperature, right? So this proposed sort of relative energy window does seem to work for these small systems. And finally, I looked at a two-level system. This is well known to have negative absolute temperatures. You can, of course, count the number of states. And this is sort of the proposed partition function in quotes. I mean, you don't really talk about a partition function, but because this is non-standard, I call it a partition function. You can plot temperature versus energy in this case. So these are the main conclusions. The Gibbs entropy misses negative temperature, as is well known. Boltzmann entropy is close to degeneracy entropy, whereas the proposed entropy again is closer to canonical entropy. The blue and the black are close to each other. So now finally, having seen the advantages of this relative energy window entropy, is there precedent for a relative energy window? Yes, there is. So there was a particular form proposed by Gurari in 2007, used recently by Burke and Huck in this PRE. So that's this form. So here somehow you are introducing the canonical ensemble into the microcanonical ensemble width. So it's constructed like that. Now I tried it, it works for an ideal gas, but for a harmonic oscillator, you get this extra term in the T versus energy relationship, right? So that's why the proposed one seems to work better for small systems. So with that, I'd like to conclude. We have an entropy definition for isolated systems considering a relative energy window. It's sort of motivated by a thermalization time that's inversely proportional to energy and the Heisenberg energy time uncertainty principle. It preserves the 0-point energy of a quantum harmonic oscillator and gives T greater than 0 for unbounded energy systems, small systems, which earlier there was a problem with Boltzmann entropy. And it also predicts T less than 0, so it sort of unifies the Boltzmann and Gibbs approaches for small systems. So thank you very much for listening. I spoke to a lot of colleagues, so I'd like to acknowledge them. Thanks a lot, and I'll be happy to take any questions.
Question?
So I'm missing something very simple, very basic. So when you talk about entropy, is essentially the idea of StatMech is to reproduce the thermodynamic entropy, and it will only care about essentially the difference of entropy between two states. So whenever you talk about certain energy window, is that you will only consider those energy windows such that which is accessible to the system and which will affect and change the thermodynamic state from one to the other, so that it can really reproduce the essential change in the entropy and not any additional constant.
Correct. Yeah. In microcanonical ensemble, we are only focusing on the states around the energy E.
Right. So even if you consider some higher energy window, which just gives you an additional constant to your entropy, but that doesn't come in the difference in entropy between two thermodynamic states, that additional constant would be irrelevant.
Yeah, it could be, but turns out it's not. I mean, it depends on the window, right? Because the entropy depends on the number of states. It's of course log of the number of states, but if you have too large a window, then you would consider too many states, right? And especially matters at low temperatures.
Even when you define states, you can ask at what resolution I will look at those states.
Correct.
And the resolution decides what's that constant that comes.
Correct.
And if
in some sense, this is sort of deciding the resolution, right? This is another way to set the resolution. Instead of a constant resolution, you have a resolution that changes with energy scale.
Okay, we can talk about it later. Right. Thank you.
Any more questions?
So the width is because the system is interacting with the world. At some point you mentioned that, right? Or yes. Is it purely because of your quantum consideration, Heisenberg uncertainty principle?
Yeah, I mean, in my understanding, and it may be different from yours, I view it as some sort of interaction with the surroundings. That's why there is an uncertainty that is coming up. Because the energy time uncertainty principle, that's how I would interpret it, that you're trying to find the uncertainty in an eigenstate, and that depends on the time over which you're observing it.
I'm conflicted by this consideration. If you have a very small system, then the surface to volume ratio is very high.
Right.
In that case, there is more. It is more appropriate to talk about how it is interact or the environment is attached to the system. Right. And another way is because it's a small system, so quantum effects are going to be more prominent. So in both ways, it comes to the conclusion that this width needs to be considered.
Right, right. Certainly. I mean, yeah, there are many ways to think about it. You are right that surface to volume ratio will be high. Surface is important. This kind of an analysis neglects the surface, but that's something which we could sort of put into the model and then see how we can include that. Yeah, these are interesting thoughts. Thank you.
Okay, so if there are no more questions, let's thank the speaker.